Hello everyone. Okay, today let's do some examples on three-phase circuits. So I'm going to start with this example. Right, so we have a positive sequence ABC three-phase source that is balanced, right? And then the line voltage is given as line or line to line. I like to call those kind of voltages line to line. It's easier to understand for me. Line could be confusing sometimes. It could mean phase. So line to line voltage is 208 minus 30. This is the voltage from phase A to B, VRMS. So this is a source that looks like this. Right, this is A, this is B, this is C. The voltage from A to B is 208 minus 30 degrees. So what would the phase voltage be? The phase voltage, we said, is just the line voltage over square root of 3. So we established that relationship between the phase voltage and the line voltage. The phase line voltage or line to line voltage is typically larger than the phase voltage, by a factor of square root of 3. So the phase voltage in this case is going to be 208 over square root of 3. Oh, this is RMS, yeah? Is 120 volt RMS. Okay. So 120 is familiar, right? 120 is the RMS voltage from the wall outlet. So this tells you that if you have a one low voltage three-phase system in a residential application, if you take the line-to-line voltage, it will typically be 208. Okay. What about now the other line-to-line voltages? What about VBC and VCA? Right. So VAB is 120 minus sorry, not VAB, VAN. Right, we said VAN. Okay, 120 is the magnitude. What about the phase? That's what I'm trying to say, right? We don't know the phase yet. We have to calculate. So this relationship allowed us to calculate the magnitude, right? Which is 120 volt RMS. But we don't know the phase yet. We have to find the phase for VAN, VBN, and VCN. We want to find those phase voltages. VBN, VCN. That's the problem. That's what you're trying to solve for. The magnitude is easy, is 120, right? What about the phases? Well, we have to do we have to do a phasor diagram first. So let's do the phasor diagram. Okay. So VAB is minus 30, right? We want to find the relationship between and we did that I think in the past, but let's redo it. We want to find the relationship between the phase voltages and the line-to-line voltages. The line-to-line voltages are just, it's VAN minus VBN. So this is the minus VBN here. It divides this angle here in half. This angle is 120. We divide it in half. So this angle is what? 60. Right? And this is minus VBN. right? So those two minus VBN and VAN have their magnitude, the absolute value of their magnitude is the same, is equal. So whatever resultant here is going to be is going to bisect this angle. So the angle is going to be 30 degrees. Right? So VAN plus minus VBN is going to be at an angle of 30 degrees. So VAN is expected to be behind VBN by 30 degrees. VAN is behind VAB, sorry, this is VAB. VAB. So VAN is going to be behind VAB by 30 degrees. From symmetry, right, the same follows for VBC. So VBN is behind VBC by 90 degrees, but by 30 degrees, and so forth, and for VCN. So VCN is going to be behind VCA by 30 degrees too. Right, so you can do this, and you will find this relationship holds. Right, okay. So if VAN is behind VAB by 90 degrees, by 30 degrees, I keep saying 90, by 30 degrees, right? So you just take the angle of VAB and subtract 30 degrees from it. So I get minus 60 degrees. Right? And then all I have to do is to find VBN and VC, and the 120 degree relationship still holds, right? Minus 120, minus 120. So to find the rest, just, or plus 120, the same thing. Sorry, plus 120 from 0. So I could take minus 60 and subtract minus 120 from it. I end up with minus 180. And then take 160 and add 120 to it, and I end up with 60 degrees. So those are the three phase voltages. I could take minus 180 and subtract minus 120. I end up with minus 300. Minus 300 is equivalent to 60. Okay. But the key thing is to know the relationship between the line-to-line voltage, the angle relationships between the line-to-line voltage and the phase voltages by doing the phase diagram. Okay. Let's do another example. So we have a Y source connected to a Y load. Where the phase voltage is 120 volt RMS. The line impedance, so there's a line impedance between the source and the load per phase is 1 plus J1, and the load impedance at the end, after the line ends, is 20 plus J10 ohms. So the question is, what is the line current and load voltage? Let's draw the circuit. Right, so I have 120 volt RMS, 0 degrees volt RMS, and then I have my other source, 120 minus 120 degrees volt RMS. Then I have my third source, 120 plus 120 degrees volt RMS. Right? And then there's a line impedance in between. There's a transmission line, right? And the impedance is just 1 plus J1. And then the loads are a Y. I'm messing it up. Cannot draw a rectangle anymore. Okay, and this is a balanced load, so all the loads are the same. So this is 1 plus J1, 1 plus J1, and then this is 20 20 plus J10, 20 plus J10, 20 plus J10, right? Now we said because this is a balanced situation, we can analyze one phase and then immediately solve the other phases, just minding that the angle relationships. So what's a single phase circuit? What does it look like? It looks like this: 120, 0 degrees, and then J, and then 1, that's the line impedance, and then 20, and then J10. Okay, so this is VAN, this is IA, this is V load, let's call it V capital A, the voltage at the load. Okay, so IA is easy. IA is just 120 over 20. The total impedance is 21 plus J. The total imaginary reactance. The reactance is 11. So you just do this math. This becomes 5.06 with the angle of minus 27.65 degrees ARMS. And then for the line, for the load voltage, you just do voltage divider. Well, I mean, we don't need to do voltage divider because we already calculated IA. You just take IA and multiply it by this impedance, and you get the load voltage. The load voltage is just going to be IA times 20 plus J10. So this is 5.06 minus 27.65 times 20 plus J10. So VA, the voltage at the load, equals 113, right? 0.19 minus 1.08 degrees, right? And just by solving the single phase in the balanced situation, we solved all three phases, right? Let's say, so you know IA. What would IB and IC be? Well, because it's a balanced situation, the magnitude is the same, 5.06, 5.06, but now the phase relationships should hold. So I can take this angle and subtract from it minus 120. I end up with minus 147.65 degrees. I don't have to do anything new. I only have to subtract the angle, and then I could take this angle now to find IC, either add 120 or subtract 120. Let me subtract 120. So I end up with minus 267.65 degrees ARMS. If I wanted to add 120, I will end up with or 5.06, 92.35 degrees ARMS. Right? And then what about the voltage at the B load, VB and VC? Well, I take what I calculated for VA and I just subtract minus 120 first, and then another minus 120, or add 120 if I wanted to. So I end up with the same magnitude, 113.19 minus 121.08 degrees VRMS, and then 113.19, another 120 minus 241.08 degrees VRMS. And this concludes this example. All right, now we want to move towards discussing delta connected sources. Right. So we discussed Y connected loads and delta connected loads, and we connected those to Y sources, but we could also have delta sources, which would look kind of like this. So we have the phase A, phase B, phase C, and now the voltage sources are between AB, BC, so there is a voltage VAB between nodes A and B. There's a voltage VBC, and then there's a voltage VCA. And in a similar manner to loads, really you cannot tell by just measuring the voltages whether the sources are connected in delta or Y, right? Because I mean, whether when you measure the voltage at node A between node A and B, it will be the same whether the load's connected Y or delta. You will get some voltage, right? So there is no this way to distinguish between them other than by direct inspection. Right? But what I'm trying to say is both are equivalent ways of supplying three-phase voltage, right? But this is the delta connected source, and we have the two line current, phase currents coming out. So we have IA, and it continues towards the load, which could be either Y or delta. And then we have IB, and then we have IC. Okay. Recall that we related the line voltage, or what's called the line-to-line voltage, with the phase voltage using the following equations. We derived that previously. So VAB is square root of VP 30 degrees, right? Assuming that the reference is the Y source, right? So the Y source starts with phase 0, minus 120, plus 120. Assuming that is a reference, then recall that we related the line-to-line voltage to the phase voltage using those expressions, formulas. So VBC is square root of 3 VP minus 90 degrees, and VCA square root of 3 VP minus 210 degrees. Right. So this is using the Y connected source as a reference. So the Y connected source was the reference. This is in the complex plane. And then we found VAB, VBC, VCA with respect to those three phase voltages. So this is VA, VB, VC. So right, so this is VAB, this is VBC, and they're ahead of VA, VB, VC by 30 degrees, and this is VCA. Right. But now we want to do something different. Now we want to select the line-to-line voltage as the reference. So I want to make the line-to-line voltage, the delta source, as the reference, meaning I'm going to just write down VAB as a line-to-line voltage with an angle of 0. I want to start with 0. And then VBC is VL minus 120. And VCA is VL plus 120. Nothing much changed here. All I did is that I changed my perspective. Instead of considering the Y source, voltage source, to be the reference, to be my reference phasors that I compare everything to, I'm using the line-to-line voltage as the reference, right? And then we could say, hey, what is the equivalent Y connection to this, to the above? Equivalent Y source to the above. Well, I mean, we could use those formulas that we remembered, right? We know that VAB is 30 degrees ahead of the line voltage, right? So in this case, that means because VAB is 30 degrees ahead, but we're starting at 0, so that means VAN, the equivalent VAN of this delta connected source, is VL over square root of 3. First, remember this relationship, VL equals square root of 3 VP, right? So VP is VL over square root of 3. And then we know that the line-to-line voltage is always 30 degrees ahead. So the phase voltage here should be behind 0 degrees by 30 degrees, so it should be minus 30 degrees. And then VBN equals VL over square root of 3 minus 120 minus 30 is minus 150 degrees. And then VCN equals VL over square root of 3 minus 240 minus 30, which is minus 270 degrees, which is equivalent to VL over square root of 3 plus 90 degrees. Minus 270 is the same angle as plus 90. So this is the three-phase Y source that is equivalent to this delta source. Right? So there is this idea of if you have a three-phase system, whether source or load, if it's balanced, you can always convert it you can always convert at will between Y and delta, go back and forth. Right? And this kind of simplifies solving balanced systems with delta connections, right? Because we already know how to solve three-phase circuits with Y sources, right? And we know how to convert from delta to Y. So all we need to do if we encounter a problem with the delta source is to convert the delta source to a Y source, and that's it. We're done. So let's do an example on that. Okay, let's do this example. As we said, I want to do an example of delta connected source. So let's see, I have a voltage source like this. This is 208 minus 240 degrees. Yeah, this is A, and this is B, and then this is node C. So between A and B, I have VAB. This is a delta connected source, so it has a value of 208, 0 degrees. Between B and C, I have another source, 208 minus 120 degrees. Those 120 degrees angle shifts between the phases must always hold for a balanced three-phase system, right? And then third phase is 208 minus 240 degrees. So this is VCA, this is VAB, and this is VBC. Right, and then this is connected to a balanced load. I'll just draw one branch. I won't draw all three branches, but they're the same. So one branch looks like this. So I have 0.1 ohms, J.2. This is the transmission line, and then this is node capital B. Right, so this represents the transmission line, and then the load is at A capital, B capital, C capital. Right, and then we have 12 ohms, J4. And typically the transmission line impedance is less than the load impedance. You don't want to dump all the energy in the transmission line. The idea is you want to dump it in the load. That's why the load has the higher impedance, or else your circuit doesn't make sense as a power delivery mechanism. Right? So we said we can convert this to Y. We can convert the delta to Y. So we can take VAB and convert it to Y. How do we convert to Y? Well, we divide by square root of 3. We take the line-to-line voltage and we divide it by square root of 3. So I have a source that's 208 over square root of 3. And then what's the next step? It's minus 30 degrees. Because the reference here, VAB, is 0 degrees. So it's going to be 30 degrees behind. So this is going to be minus 30 degrees. And this is a single phase. Right? So now we can do this. We can solve single phase, 12 ohms, and use that to get the currents and all of that. So this is exactly the same as previous example. The only difference is that we started with a delta connected source and we converted it to a Y source. So I don't want to go through it because we're essentially repeating the same thing. Okay. Now let's talk a bit. So we talked about Y source, delta source. Right. Let's talk about delta connected load. Okay, so again, we have three phases, and we are agnostic on whether those phases are line to line or Y or delta essentially. But I mean, we can, whether it's Y or delta, we can always find the equivalent Y and the equivalent delta. That's fine. So let's assume it's Y, VBN, VCN, right? And this is equal to VP, 0 degrees. This is equal to V phase minus 120 degrees. This is equal to V phase plus 120 degrees. Okay, and this goes now into our load, IA, IB, and then IC. But this time around, our load is a delta connected load. So our load looks like this. Z delta. And it's balanced, so the load is the same for every branch. Z delta. So I have IAB, I have IBC, then I have ICA. Okay, and then we said we can, hey, convert, this is a Y source, we can convert it into a delta source, and that's easy, we already derived that. That's square root of 3 VP, 30 degrees, VBC equals square root of 3 VP. We're repeating ourselves at this point, but just to emphasize. Square root of 3 VP minus 210 degrees, minus 240 plus 30. Right? Now, what is IAB in this case? IAB is clearly, why did I calculate VAB? I calculated VAB because it will make calculating IAB easy, right? Because VAB appears across this impedance, Z delta. So that allows me to directly calculate IAB. IAB is going to be VAB over Z delta. That's it, right? And clearly, I mean, IAB depends on right? IAB is proportional to VAB, IBC is proportional to VBC, and so on and so forth. So that tells me that the same relationships that hold between VAB, VBC, and VCA are going to hold for IAB, IBC, and ICA. So in the same manner that the angles are 120 degrees between VAB, VBC, and VCA, and the magnitudes are the same, in the same manner from this relationship, it's clear that IAB, IBC, and ICA have the same angle relationship, have the same 120 degrees relationship, and their magnitudes are the same. Right? And this is how we calculate each of them. IAB is VAB over Z delta, IBC is VBC over Z delta, and so on and so forth. What about the line currents, IA, IB, and IC? Well, those we can calculate from KCL, right? So clearly, IA coming in equals IAB coming out minus ICA coming back into the node, right? So we just apply KCL on those nodes. and we get the line currents. So in this case, IA equals IAB minus ICA, right? IB, this one, equals IBC minus IAB. So this is IBC minus IAB. And then finally, IC, this current, IC, equals ICA minus IBC. So this is one way of calculating the branch currents. If you know Z delta, you can calculate those currents, subtract them from each other like in this manner, and you get the line currents. Right? There is another way of doing that. We can take the delta load and we can do a Y we can do what's called delta to Y transformation. Right? So we can convert this into a Y load essentially. Right? And we will find that for the balanced case, we can do that for the balanced case only, right? For the balanced case, the equivalent ZY is going to be 1/3 Z delta. Right? But we don't have to take it as a matter of faith. I mean, let's derive this. Let's derive it. Derivation. Okay, let's do that. All right. So we said, hey, we want to find the equivalent impedance, the equivalent Y impedance to Z delta, such that if I take IA times ZY, what should I get? I should get VAN, right? So here I'm taking this delta load and I'm converting it to a Y load. What happens if IA goes into the equivalent Y impedance? This is N here, right? Well, this is at the same voltage as the neutral. This is a neutral, right? Remember, this is a balanced situation. So we get this voltage drop across this resistor or impedance is going to be just VAN, right? IA times ZY. So we should expect that whatever my equivalent impedance to the delta, this is what I'm trying to calculate. I should expect this times IA to give me VAN. But I know already what IA is from this equation, right? So IA is going to be IAB minus ICA ZY equals VAN. I know now what IAB is, right? IAB is just VAB minus VCA over Z delta, right? We also know that this fact, right? This is what IAB and ICA is. So I can take this Z delta out and I end up with ZY over Z delta. Right, so I can rewrite, that's what I'm solving for. I'm solving for ZY. So ZY then equals VAN over VAB minus VCA Z delta. Assuming my reference is the Y source, I can write VAN as VP 0 degrees. And because my reference is the Y source, VAB can be written as square root of 3 VP 30 degrees, right? We already did that, derived that. We know that if the Y source is the reference, what the line-to-line voltages will look like, and both their magnitudes and their angles. And VCA is minus square root of 3 VP minus 210 degrees. VP cancels. Oh, this is Z delta. and we end up with 1 over, take square root of 3 out, 130 degrees. What's 130? Well, let me write it down. 130 degrees minus 1 minus 2, 10 degrees. It's just a complex number now I have to solve. When I solve this, when I calculate this complex number, it will turn out to be 1/3. So let me show that. Right. So it's going to be square root of 3. Now this is just cosine 30. Cosine 30 is square root of 3 over 2 plus j sine 30, which is half, and then minus, right, and then this is cosine minus 210, which is, if you do get out the calculator, this will turn out to be minus square root of 3 over 2, but minus minus, because there's a minus here, becomes plus square root of 3 over 2, and then minus sine minus 210, right, which turns out to be j half. Z delta. Okay, so yeah, if you go to calculator and do sine minus 210, you'll get half, and then there's a minus sign here, right? So this will turn into a minus. Okay, the idea is that now this cancels with this, and we end up with 1 over 2 square root of 3 over 2, which is square root of 3. So 1 over square root of 3 times square root of 3, which is 1/3 Z delta. And this proves our relationship. Right, and if we have Z delta, we can find the equivalent ZY, and then we can use this ZY to just calculate the line current. The line current is just going to be the VAN over ZY. So it simplifies things a bit. What would what I wanted to say? Okay, so can we relate in the same way we related the phase voltage to the line voltage? Right, remember the line voltage was square root of 3 of the phase voltage. What is the relationship between the line current and the delta current? So if I have a line current IA, IB, IC, all phasors going into a delta load, right, so magnitude of the current here is I line, let's call it the line current, and the magnitude of the current here is called I delta, the delta current, the current in each of those delta branches. Right? In the same manner, in the same way we found this relationship, we can find that, hey, IL magnitude is equal to square root of 3 I delta. Right? It's exactly analogous to what we did for VL and VP. And to see that, right, so IA equals VAN over ZY, right? So the magnitude, what's ZY, right? We said ZY is 1/3, so it's going to be 3 VAN over Z delta, right? That's the relationship between ZY and Z delta, right? And then right, and then VAN is just so this is I'm just interested in the magnitude, by the way. So the magnitude of IA is IL, so IL is just what's the magnitude of VAN? The magnitude of VAN is just V phase, right? V phase, 3 V phase over magnitude of Z delta. But what is Z delta? I think we have the equation above here somewhere, right? Z delta is just VAB over IAB, right? So the magnitude of Z delta is just the magnitude of VAB over the magnitude, it's this equation, see? So it's the magnitude of Z delta is just the magnitude of VAB, which is the line to line voltage, over the magnitude of the delta current, right? So it's the magnitude of the voltage over the current, right? So Z delta, magnitude of Z delta is just the magnitude of the line to line voltage, which is VL, over the magnitude of the current, delta current, IAB, which is I delta, right? But we already know, so this is going to be 3 VP I delta over VL. We know the relationship between VP over IL, right? So VL is just square root of 3 VP, right? So VP cancels with VP, and then 3 over square root of 3 gives me square root of 3 I delta. So I just proved this expression here. Okay. Let's do an example. Okay. So we have a balanced delta load consisting of 10 ohm resistor and 20 millihenry inductor, and then we have a Y source, again balanced, with VAN equals 120 30 degrees. That's what VAN is. Right? So we want to find all the delta and line currents. Right? So this is the load. The load is delta, and there are a bunch of line currents. We want to find the line currents 1, 2, 3, and the delta currents 1, 2, 3. Okay, so solution. Well, I mean, we are directly given the impedance, right, for the delta load. So Z delta is just a resistor plus J omega L, so 2 pi 60, 20 millihenry, 20 times 10 to the minus 3, so this is omega L. If you crunch the numbers, you get 10 plus J 7.54 ohms. Right? So VAB, we're given the phase voltage. I want to calculate, because this is a delta load, it's easier to calculate the delta current. Is easier to just find the line to line voltage, which is VAB, which is just VP 120 times square root of 3. And then we said VAB is, remember, is always 30 degrees ahead. So if I have VA, VB, VC, VAB is always 30 degrees ahead. Right? So I need to add 30 degrees to VAN. So I end up with 60 degrees here, VRMS. Oh, this is VRMS. Okay. And now I can calculate the delta current. The first delta current, IAB, is just VAB over Z delta, which is equal 120 square root of 3, 60 degrees over Z delta, which is 10 plus J 7.54. Take out the calculator, and this becomes 16.6, 22.98 degrees amps RMS. Okay, now I want to find the line current, and it's easiest to find the line current. It's easiest to convert the delta load into a Y load. So the Y equivalent of this delta load is just going to be 1/3 Z delta, which is going to be, let's see, yeah, what's 1/3 of 10 is about 3.33 plus J 1/3 of 7.54, which is about 2.513 ohms. So IA in this case is going to be VAN, the phase voltage over ZY. Again, this is a balanced three-phase circuit, so I can consider one phase at a time in the Y circuit, and this becomes 120, 30 degrees. That's my VAN over 3.33 plus J 2.513. Take out the calculator. 28.74 minus 7 degrees ARMS. Okay. Now, again, because this is a three-phase problem, all we need to do is calculate one line-to-line current, one delta current, and one phase current. The other two are the same. They have the same magnitude with a different angle. Right. So the other two delta currents are as follows. So I BC, and then there's ICA, right? IBC is the same magnitude. It's going to be 16.6, but then now the angle is going to be shifted by 120 degrees, minus 120 degrees actually. So 22 minus 120 is about minus 97.02 degrees. ICA is going to be 16.6. I'm going to take this angle and add to it 120. So minus 120 plus 120. So it's either minus 120 minus 240 or minus 120 plus 120. So it's going to be 142.98 degrees. And then IB, the line currents, the other two line currents are going to be the same as this. 28.74 minus 120 is going to be minus 127.01, and then IC is going to be the same magnitude minus another 120, or plus 120 is going to be, I mean minus 7 plus 120 is going to be plus 113 degrees amp RMS. Right, and yeah, so this concludes the example. Okay, so before we move on, I wanted to go through the summary that's presented in the textbook that shows the Y load and the delta load, and it shows the relationships between the line voltages and the line voltages, the line-to-line voltages, the phase voltages, and the line currents and the delta currents. So you can see here, this is the phase voltage for a Y connected load, and then this is the line-to-line voltage, and you see the relationship between them, square root of 3. Right, and then the angle relationship is plus 30 degrees. So if the phase voltage is at angle phi, any random angle phi, then the line-to-line voltage is going to be the same phi plus 30 degrees. And of course, going from this phase to the rest is going to B and C is just going to be a matter of adding 120 degrees. And the same way here, this is the summary for the delta connected load. So you can see that assuming that the line-to-line voltage is at phi, which is the phase equivalent phase voltage, assuming that the Y connected equivalent is the reference. So it's going to be phi, which is for the one for the Y equivalent voltage, right, plus 30 degrees, and then this shows the angle of the current. Going to be also plus 30 degrees, and then the other two phases are going to be plus 20, minus 120, plus 120, and so on and so forth. Right? So this table kind of summarizes all those relationships. So the line voltage for the Y configuration And for the delta configuration, for the delta configuration, it's just V line to line. For the Y configuration is going to be square root of 3 of the phase voltage, right? And then the line current, the phase voltage, and the phase current. Right. So the phase voltage for the delta is just the line-to-line voltage. That's what it is, because the phase in a delta connection is the line-to-line, is across the line-to-line. Right? Phase current and load impedance. And you can see here the delta is 3 times the y. So we maintain the relationship that z y equals 1/3 z delta. Okay, so we are done with the three-phase sources and loads, Y and delta, and their different connections. And it's time to move on to power relationships, which we will do in the next lecture. Thank you, guys.